from across the globe, from the centre of aerospace. And now to you.
Thank you for downloading the Aero Society podcast from the Royal Aeronautical Society.
Good evening, everyone. Welcome to this Royal Aeronautical Society Heathrow branch webinar. My name is William Lee, and I'm the Honorary Secretary of the branch and the moderator for today's session. Joining me today is our speaker, Dr. Val Mikov, founder and CEO of ZeroAvia, and our branch chairman, Miftakhov, who will be hosting today's webinar. Before I hand over to Peter, there are a few housekeeping points that I would like to make. First of all, please feel free to share your thoughts about today's event on social media channels such as Twitter by @RAeS LHR and using the hashtag RAeS LHR event to interact with us. Secondly, if you require a CPD certificate of attendance for your own initial or continuing professional development records, please use the Q&A panel now to inform us your name, and we will email this to you post-event. Your microphone is on mute, but throughout the webinar, we do encourage you to use the Q&A panel to raise any questions that you may have, and you can also interact with us by clicking the thumbs up or like button next to each questions that are being published. Finally, I would like to make you aware that today's session is being recorded and will be made available via our podcast and YouTube channel afterwards. So without further ado, let me hand over the foreplay to Peter.
Thank you, William, for that introduction, and to Air Chief Marshal Sir Brian Burridge, the Chief Executive Officer of the Royal Aeronautical Society, for his personal message to us. Hello, everyone. I'm Pete Fryer. I'm the chairman of the Heathrow branch of the Aeronautical Society, and I'm exceptionally pleased to be able to welcome all of our viewers this evening to the third of this season's branch lectures, all presented as webinars. Unfortunately, I've been unable to act as the moderator and chairman of the previous two branch meetings due to technical difficulties. That's now resolved, and I'm at last able to greet you personally to this season's lectures. I'm able to check that you're in good health and to wish you all my very best wishes. Thank you to Anna Pedraz, our Vice Chair, for so ably undertaking these duties in the past. We look forward and will continue to share the role together. So, this is the first chance I've had to speak with you, the branch membership, since I circulated my chairman's statement and newsletter in August this year. In that statement, you'll have seen that during this year's virtual Farnborough International Trade Show, the UK government made most important announcements concerning the setting of new national strategies in the area of robust and strengthened green and sustainable future for the aviation industry, supported by significant central funding of the development of these new technologies. This was to be accomplished by sponsoring the recovery of our industry from the COVID-19 disaster by changing the environmental footprint of the aerospace sector, i.e. by altering the face of aerospace development and operations by making the United Kingdom a world leader in sustainable technologies such as sustainable aviation fuels, clean burning fuels such as hydrogen or ammonia, hybrid electrical propulsion, wholly electric propulsion, urban or advanced air mobility environments, technologies and vehicles. The intent of this was to bounce back with an aerospace industry bigger and better than it was before, which will be friendly to our strained environment with more ecological morals. Webinar strategy sessions were held during the Farnborough week, during which the government pledged enormous sums of money to sponsor Indigenous development of the necessary technologies and engineering. The Department of Business, Energy and Industrial Strategy and the Department of Transport took leadership actions in setting up and empowering committees and working groups in the UK Aerospace, Defence, Security and Space Industries Trade Body, and in the associated non-governmental academic and research and technology organisations such as the UK Research and Innovation Industrial Strategy Challenge, the Aerospace Technology Institute, the Knowledge Transfer Network and many more. As part of this branch's future, we will be playing our part in this initiative by placing additional emphasis this year in briefing you through focus on this year's lecture programme. Tonight, I'm excited to have secured a rather important speaker to brief you all. It's Val Mikov, who, despite being a household name to me, if you've not already heard of him, you will have in the very near future. Val holds a PhD in physics from Princeton University, a master's in physics from the Moscow Institute of Physics and Technology, and was a double winner of Russian nationwide physics competitions. He's held a number of senior business and product positions at Google and McKinsey, and was a nuclear researcher at the Stanford Linear Accelerator. Val is a serial entrepreneur in the electric vehicle space. His previous company, Motorwerk, has developed the world's leading platform for electrical vehicle battery aggregation to provide grid services, and was acquired in 2017. Most importantly to us, as aeronautical engineers and aerospace industry professionals, he is currently the founder and CEO of ZeroAvia Inc. ZeroAvia is a company set up in California, with its major operations based in the UK at Cranfield Aerodrome near Bedford, co-located at the home of the world-famous Cranfield Aeronautical University. ZeroAvia is developing the world's first practical zero carbon emission aviation powertrain. You will no doubt have seen the news headlines in June this year, generated by the maiden flight of the UK's first ever electric powered commercial scale aircraft, a 6-seat Piper PA-46 Malibu aircraft modified with an approximately 300 kilowatt battery and an electrical propulsion system. In September, that aircraft's further modification enabled the world's first flight of a hydrogen-fueled commercial-grade aircraft. That is, to use a hydrogen fuel cell to convert hydrogen fuel to supply the electric power, leaving nothing but water and heat in its wake. ZeroAvia has ambitions to develop and prove a family of progressively higher powered hydrogen fuel cell powered powertrains, perhaps in 250 kilowatt increments, to progressively support and power 18-seat, 50-seat and bigger hydrogen powered aircraft development, all done by aircraft airframers. As recognition of his credentials and his importance in the sector, Val was invited by the UK government to have a permanent position on the 2050 net zero target ZeroJet Council, jointly chaired by the Right Honourable Grant Shapps MP, the Transport Secretary, and the Right Honourable Alok Sharma MP, the Business Secretary. Val holds an aeroplane and helicopter pilot's licence, which he makes excellent use of during his spare time. In this session, Val Miktakhov will address the scope of carbon emissions generated by the aviation sector and the challenges the industry faces in reducing emissions with existing solutions, and discuss the benefits of electrification for aviation. The company's breakthrough hydrogen-fueled electric powertrain technology will enable a 100-seat aircraft by 2030, beginning with a 19-seat zero-emission aircraft operating commercially by 2023, no time at all, dramatically faster than the industry experts anticipated. He will also outline what further engineering efforts are required for hydrogen electric planes to power larger commercial aircraft. To all of our audience this evening, if you have any questions for Val, I encourage you to pose them through the Q&A window, which can be opened from the question mark button on your screen. I will now pass over to Val Miktakhov, who, following a short video presentation, will present his lecture, Solving the Aviation Sustainability Problem, starting in 2023. Val, a very big welcome to the Royal Aeronautical Society's Heathrow branch. Over to you, William.
ZeroAvia is revolutionizing aviation by building a new generation of zero-emission powertrains for aircraft of all sizes. So we're hoping to become one of the major engine manufacturers for the new sustainable aviation. That was great. Thank you for running that video. This is Val Mikov, CEO and founder zero-emission aviation startup ZeroAvia. Great to be here, and thank you, Peter, for such a great introduction. I heard that there's a great amount of interest in what we're doing and all the progress that we have made up to date. So I will talk a little bit about why we're doing what we're doing, and how we're doing what we're doing, and what we have done so far, and what's coming in the very near future. So hopefully you will enjoy the walkthrough, all this story, and then we'll have a nice Q&A after that. So overall, you've seen this, I'm sure, multiple times before. Starting about 2 years ago, 2 or maybe 3 years ago, really we've seen the beginning of sustainability drive in aviation. And one of the catalysts for that, of course, was Greta Thunberg, who famously went on the climate strike and was talking about climate change in general, but also very pointedly about the aviation impact in that. And practically started and expanded the flight shaming movement that actually results in a sizable reduction in flights in the Nordics, at least, and in some other countries as well, which only highlighted the size of the problem and the importance of the problem, that is climate impact of aviation. In a more quantitative terms, what you see on the slide here is the problem that this presents in terms of the overall human climate impact. Even right now, we already see between 5 and 10% of total human climate impact being from aviation. About half of that is because of the CO2 emissions. Another half is other forcing mechanisms from nitrogen oxide, from contrails formation, from cirrus cloud formation. The range, the estimates vary, but generally speaking, between 2 and 3x of the carbon emissions impact alone is what's attributed to the aviation impact for high altitude emissions. If you just look at the business as usual scenario, growth scenario, and let's not think about pandemic for a bit. We're going to get back to the growth rates that we have seen, I'm pretty sure, within the next 2 or 3 years. If you just project that to 2050, when everybody, all the countries, all the industries want to be decarbonized, zero emission, no climate impact, aviation would grow 3 to 4x in emissions and can become 25 to 50% of total climate impact by humans. And this is, of course, something that we just cannot allow to happen as an industry. What makes this problem even harder is the fact that the useful life of commercial aircraft, as we all know, is about that period of time between 2020 now and 2050, 30 years. The aircraft that's built and bought new today will probably be just retiring in 2050. So that means the problem is actually really happening right now, needs to be starting to seeing a solution right now. But unfortunately, we don't really see real, truly scalable solution today. So that was the motivation behind starting the company about 3 years ago. And we said very early on, we want to really focus on the commercial aviation, not just what was in vogue back in the time, urban air mobility, vertical flights, which are all very exciting things on the technical perspective, but they're not the ones that would bring the emission benefits today. Over time, however, the air transport is expected to go into wider and wider segments, and essentially, the fundamental reason is that only air transport is truly 3D scalable. So on the bottom right here, those who recognize the picture from a Fifth Element, the movie, get bonus points. But we're going to see some version of this sometime soon, and we need to make sure that when that happens, all of those flying vehicles are propelled by zero-emission fuels. So how are we going to do it? There are multiple ways to do it, of course, and we'll go through several. All of these in the next few slides. Batteries, one of them. That's the first picture here. The turbine electric hybrids is a possibility. Biofuels, synthetic aviation fuels, direct air capture or concentrated CO2 sources, producing liquid fuels, possibility. Direct hydrogen burning turbines, a possibility as well. And finally, the hydrogen fuel cell based hydrogen electric aviation. So how do we make sense across all of this? And this is something that we had to actually do early on at ZeroAvia. We looked at fundamentally what are the first principles behind each of these propulsion methods, each of these fuels, how we think they will play over competitively with each other, perhaps, and competitive with the jet fuel, with the fossil fuel, over the next 10, 20 years, 30 years, and what we think is going to win in the end, or what's going to take a significant portion of the market. So let's look at these one by one. On batteries, of course, and as Peter mentioned, my previous company was in the electric vehicle space, in the battery EVs on the ground, and we've done a pretty good job at working with a number of automakers and a lot of the charging infrastructure companies out there to integrate 100,000 plus, I think, is the number right now under our platform, 100,000 plus vehicles. All these batteries on wheels to help integrate more renewables into the grid, provide grid services, grid resilience. When the power goes down, you might possibly get the power from your electric cars in your neighborhoods, all those things. So we know as a team, and I have several key people on my team today at ZeroAvia coming to the team from my previous company. So we know very well the batteries and the battery advantages and disadvantages. So some of the disadvantages mentioned here that are relevant for aviation. Batteries are dramatically heavier than jet fuel on a per unit of energy. So here, 250 watt-hours per kilo is something that the best production battery of today can deliver. And this is a Tesla Model 3 battery pack. And this is at the cell level, right? So we're not even talking about the overall battery enclosure, battery management system, cooling systems, thermal management, fire prevention, all of those things, right? So 250 watt-hours per kilo versus 12 kilowatt-hours per kilogram for jet fuel. So 50 times the difference. And yes, of course, the efficiencies of transferring that energy into propulsion are different, but the starting point is 50x. Then the other problem the batteries have is high cycle costs. And this is actually often not really mentioned in the analysis, various analysis that people do of relative options. And this is really dramatic in the commercial aviation. So typical high energy battery would have maybe 1,000, maybe 2,000 cycles before it degrades. Let's say 20% is a typical metric that people use. When battery degrades 20% or more in terms of capacity, it is considered out of cycle life. And it's probably cannot be used anymore in a flying vehicle or in a moving vehicle where total energy capacity is so important. Now, 1,000 cycles is a great cycle life for a personal car, which will probably mean you can have 200,000 miles, 300,000 miles of total resource, which is more than people typically drive in their vehicles. An average vehicle in the United States sees only about 150,000 miles, maybe 140,000 miles before it's completely done. But for commercial aviation, if you look at the regional aviation, where we're going to see first adoptions of these technologies, it's not uncommon to see vehicles that perform 6 or 8 flights a day, 3 or 4 round trips, each of them maybe less than an hour, maybe 40 minutes. And if that's a cycle on your battery, and you have 8 cycles a day, your 1,000 cycle, you can do the math, it's less than half a year. And that's just driving a lot of costs and actually materials and recycling problems. And one other thing that a lot of the analysis don't actually take into account is the fact that you do need completely new fuel infrastructure for battery electrics. Of course, you need it for any new fuel, hydrogen included, but a lot of times when we see the analysis in the press and whatnot, people assume that because electricity is everywhere, in the wall socket everywhere, at the airports included, then we have enough electricity to power the electric flight as well. And this could not be further from the truth. The amount of electricity that you would need basically doesn't exist anywhere at the airports, not even the largest airports. They just don't have the supply. So you would have to bring in new supply, bring in new infrastructure. So this is, of course, a challenge. So that's a battery story. Basically, what it says is maybe for short trips and low utilization scenarios, we might see them in aviation. And of course, everything improves and the batteries improve and they become better and cycle life becomes better and the energy density becomes better. And that means that the segment that the batteries can cover will increase over time. But the gap is just so high between that and the jet fuel. Next one actually helps that a little bit, where we say, okay, the batteries are too heavy, so why don't we combine the turbine that uses the fossil fuel and a little bit of battery just to help it out a little bit, maybe on takeoff, so we can downsize the turbine, maybe for cruise, and get some more efficiency out of this, and maybe some lower emission on the takeoff stage of flight and initial climb out. Possible, scalable. The problem is that, of course, higher weight and complexity by construction. You're adding new systems, you're adding a battery, you're adding the motor generator, power electronics, wiring, all of those things, right? So you're adding that, adding complexity, which makes it harder to certify, of course, is a more complex system. But by the time you take all of that into account, all that extra weight, you will actually see that there are relatively minor improvements in efficiency. And there are various studies out there. There's a NASA study out there that says, well, by the time you actually take into account all those effects, you're going to see maybe single-digit % improvements in efficiency, which is okay, but definitely not going to solve our big problem that we have in aviation. We really need to drastically reduce the emissions. So the hybrid's probably not going to do it. Additionally, retaining high maintenance costs on the turbine still. So you run a turbine, high pressure, high temperature, familiar to all. Now you're running a smaller turbine, which is less efficient, generally speaking, and probably has shorter maintenance intervals as well. And you still retain some of the non-CO2 effects of the climate change. So nitrogen oxide is still there. Sulfur oxide, perhaps, and soot particles, especially if you use conventional fossil fuel. So turbine hybrids, incremental improvements, scalable, so it's a technically sound solution, but only incremental improvements in efficiency on the fuel. So the next one is biofuels. And that's where most of the sustainable aviation fuels are in right now. It's of course zero emission, zero CO2 emissions, and actually better particulate emissions as well, often, obviously much lower sulfur content, so you don't have that much of the additional emissions. But the core problem there is scalability, and the root cause for that is, and that's a comparison that I like to make. For biofuels, if you take two equivalent land plots in a, let's say, Southern Europe or Southwestern United States, where there's a lot of solar resource, and plant feedstock, biofeedstock for biofuel on 1 acre of land, and next to it you put solar panels and the electrolysis machine that produces hydrogen out of water and electricity, you will have 500 higher yield in terms of the chemical energy in your fuel from the solar electrolysis 1 acre of land than you would get from the biofuels feedstock. So that kind of makes it clear that once you try to scale it really, let's say you want eventually 100% of aviation, and aviation is growing. Once you try to scale it to that type of scale, you will run out of water, you will run out of land, and it will just not be economical at that point. And on top of that, of course, you still have relatively low efficiency of the thermal engines, especially on the bottom end of the spectrum for smaller vehicles. Still some artifacts of high temperature combustion like nitrogen oxide and so forth, and a higher maintenance cost generally than electrified powertrains. So synthetic fuels, the next one. Synthetic fuels are actually scalable. So you can have a hydrogen feedstock from renewable electricity, so that you can produce at scale, as mentioned just in the previous slide. And then you can combine it with the CO2 from, let's say, direct air capture or concentrated industrial sources, and produce liquid fuel, liquid jet fuel, synthetic jet fuel. That actually can scale. The problems are that it's quite a bit higher cost of production, because compared to hydrogen, for example, because you have to start from hydrogen feedstock. So you're already invested into infrastructure for hydrogen. You produced hydrogen, and then you have to get CO2 from direct air capture, which is a pretty expensive process and it's resource intensive. And then you have to have another chemical plant on downstream to combine the two and produce the synthetic fuel. And then in the engines, you're still retaining relatively lower efficiency, high maintenance costs, and all of the artifacts of high temperature combustion. So synthetic fuels, scalable, but costly, and still have some disadvantages of internal combustion engines. And then we're moving to the two hydrogen-based sources. So hydrogen turbines, an interesting approach that produces sort of true zero emission outputs. So it's not a net zero emission, but true zero emission out of the engine. Perhaps some nitrogen oxide still there because you do have high temperature combustion. In fact, if you don't manage the fuel oxygen mixture correctly, you're going to have even more NOx than a kerosene turbine or jet fuel turbine. But you can manage the ratio of hydrogen to oxygen to reduce the flame temperature, which also reduces the efficiency, of course, and reduce the NOx production. You still have relatively lower efficiency in the thermal engine than some of the electric powertrains, but at least you're avoiding the soot particles, you're avoiding the CO2 emissions, and some other effects. Now, it does require new fuel infrastructure. Similarly to battery electric, new fuel, you need to produce it, you need to deliver it, you need to figure it out. And one other disadvantage of this hydrogen in general, really, but in this specific case of burning hydrogen, even more so, is the high volume of fuel. So hydrogen is, of course, more energy dense per kilogram than jet fuel, 3 times better, right? But by volume, it's actually 3 times worse, because hydrogen itself, even in liquid form, cryogenic liquid, is 10 times less dense than jet fuel. So kilograms per liter, right? 80 grams per liter versus 800 grams per liter or so. So that means that your 3x advantage on the energy per kilo gets divided by 10, becomes 3x disadvantage on the volume. And if you want your aircraft to fly the same distance and you want to burn hydrogen in a turbine, then you're going to need 3x more volume to go through the same distance. So that reduces the possible range of aircraft. And that's where we come to what we think is the best option, which is hydrogen fuel cell based approach, hydrogen electric. So you do have higher volume of fuel, but you are using it more efficiently. The fuel cells today already, even the smallest fuel, well, not the smallest, but the ones that we use, which right now we're running this, as Peter mentioned, and you saw in the video, the 6-seat 2-ton vehicle. It's a 250 kilowatt system, which we're scaling now to 600 kilowatt turbine replacement engine. Even those smaller fuel cell systems are over 50% efficient, which is, compared to a small turbine, is easily 2x more efficient. So you get, remember from the previous slide, you get 3x disadvantage on the volume. Now you get 2x of that back for a small turbine or small aircraft. So you're only about 1.5x more volume requirements, which gets to a manageable point, right? And remember, on the mass, you're always better, right? Now you're becoming competitive on the volume, which is important. So you can see how you can deliver similar ranges from the hydrogen electric aircraft compared to the fossil fuel aircraft. The disadvantages are lower power density. Today, the turbines are great. Even the small turbines like PT6 turbine is achieving per kilogram. The best fuel cell systems of today are maybe at best 1 kilowatt per kilogram. That's the one that we are roughly flying today. That's including, you know, the fuel cell stack itself, balance of plant, all the compressors and everything all together need to be coming together to make this happen, which is better than piston engines. But really, you know, if you want to go to commercial aviation, you need to beat the turbines. So we have some ways to go there. And of course, new fuel infrastructure is required, right? You need to get hydrogen somewhere, delivery or on-site production. That's new fuel infrastructure. So out of all of this, and we did this like behind every slide here, there is a very extensive analysis with a lot of people involved and third parties and all of that. So out of all of this, we decided that the best approach really is renewably powered hydrogen electric aviation. And that's what we set out to do 3 years ago. We think that it can deliver not only zero emissions, but also lower costs and long range that can be competitive with the fossil fuel aircraft. We believe that the best approach to the infrastructure side is renewably produced hydrogen from near-site renewable electricity, ideally on-site production through electrolysis at the airport, whether roadside or airside, but at the airport, so we avoid transportation of that fuel. Transportation of that fuel, remember, higher volume drives costs of the fuel quite high, and we want to avoid that. So that's the approach there. It was good to see over the last, especially 6 to 9 months, a huge acceleration of hydrogen in aviation. In May, there was a study that was released by the Clean Sky Initiative and European Union that basically said the future of aviation is going to be hydrogen. And then we saw French government and Airbus making escalating level of commitments starting early this year, and then going to, in the summer, ZeroAvia, we held our own aviation sustainability summit in summer, and we had Airbus and Rolls-Royce and others present there, and Airbus started talking about hydrogen as one of the primary vectors for them for cleaning up aviation. And then I was in the panel with Guillaume Ferry just a couple of months ago when he was very strongly committing to hydrogen for Airbus as a solution. And then, of course, about 7 weeks ago, we heard Airbus make an announcement about 3 new airframes that they're targeting for 2035 entry to service that are designed for hydrogen specifically. So it was great to see just in the last 9 months such great validation for the hydrogen strategy. But we think it's going to be even better than that. We think that not only hydrogen is better, or hydrogen electric is better than anything else in the zero emission space, it will be better than jet turbines eventually. It's similar sentiment to what we've seen in ground mobility, right? So the EVs are better cars than gasoline cars. So not just, best zero emission cars, but they're better cars. And that's what Tesla realized early on, and they built a better car. Those cars are selling because they're better cars. They have better user experience. So similarly here, we think that there are some advantages that hydrogen electric approach actually has over jet turbines. Some of them are here, not going to read through the whole thing, but the fuel cost is much more stable because fundamentally electricity is much more stable commodity. And if you hook up your fuel production facility to renewable electricity, it is usually sold on a long-term contracts, fixed price PPAs that make for a very stable fuel cost in the end. And then you can also make that cost significantly lower than jet fuel. Of course, depends on where you are with the jet fuel, but we're seeing $1 to $1.5 per gallon equivalency within the next couple of decades. Right, and 3 years out, we're seeing a possibility to beat the jet fuel price for small operators because of that wider efficiency gap and generally higher cost of fuel for small operators, small aircraft. You're going to see lower maintenance costs, especially for small turbines, small aircraft. We're talking about much longer times between overhaul or major maintenance. You're going to see a lot of the on-condition type maintenance requirements because naturally these powertrains are fully instrumented with data capture and analysis. You're going to see lower noise levels. You're going to see more efficient airframes enabled by this electrified propulsion because it's easier to distribute now the source of thrust. Now that you have electric motors. So we think that overall is going to be a better product over time. So what we're working on, obviously a family of engines, but this is something, let's say, maybe a couple of steps out in the future that we're putting together that looks a little bit familiar perhaps, but what it is a vision for a highly integrated aircraft engine that instead of a familiar turbine, you have the fuel cell stack cores and the electric motors integrated with the power electronics, complex heat exchanging, and here it's shown with reaction engines heat exchange concept that we're working with them on. And we think that level of integration is going to really bring out the much higher power densities that will become competitive with the jet engines, with the turbine engines. Obviously, storing fuel is very important, and we're working with some partners on that that show pretty amazing mass fractions for the fuel storage. So this particular one, this is not a Photoshop. This is actually how much it weighs, the tank that is shown on the picture here. You get 70% mass fraction, which means that 70% of the total mass of your storage is fuel, right? And for hydrogen, this is very, very high. And if you remember, by unit of mass, hydrogen is 3 times better than jet fuel. So now if you have 70% mass fraction, that means that by mass of the entire fuel system, you're 2x better than jet fuel. So you can trade it, for range, or you can say, well, I need the same range, but I'm going to now have 1/2 of the weight of the fuel that I would otherwise need, which opens up interesting possibilities, of course. And then we talked about the infrastructure, and our approach as a company is not only provide the power plants on the power by the hour sort of hourly lease model, but also include in that power by the hour, include into that business model the fuel cost. So we will also look to control the fuel supply and deploy these fuel generation facilities on the airports. We actually have one at Cranfield already built up, small scale, but it creates hydrogen for our operations and powers our planes. But imagine, those of you who may be familiar with, what Tesla did with their supercharger network, that basically is considered to be the main selling factor for Tesla cars, because that removes completely any range anxiety from the equation for all the drivers. They know that they can get get electricity in any place in the world by just driving through the supercharger and charging for 10, 20, 30 minutes. Same concept here. You need to enable ubiquitous fuel. So our plan, roadmap, starting with 10 to 20 seats, sort of PT6 size replacements, so 600 kilowatt or so, going after aircraft like this, Part 23 initially up to 19 passengers. We believe that within the next 3 years, we'll be able to deliver 500 miles of range in those types of airframes, which already covers a vast majority of use cases for those airframes. You generally, as a passenger, you don't want to be there for more than an hour in the aircraft like this. So that's the type of missions those aircraft fly. And there are about 10,000 of those aircraft worldwide. So it's already a quite sizable market. But that's obviously just the beginning. And then we move to a larger airframes, longer distances. We think that by 2030, we actually can fulfill the Prime Minister's vision here and the Jet Zero vision of a single aisle 100 passenger jet being able to go for 1,000 kilometers. In his case, we think that target can be actually improved. We think that we'll be able to do 1,000 miles by 2030 and put it in the air. And then beyond that, you would need to see some new aircraft concepts. So this is an older version of this slide that did not have yet the new concepts from Airbus. So it was great to see Airbus actually announcing the new concepts that they are going to build 2035 plus, and that's what would be fitting here. Now, we're not just talking about those things. We're actually making these things happen. So on the R&D roadmap, we're already flying 6-seater aircraft. As you know, this is now world's largest hydrogen electric aircraft. We have flown first flight September this year. We then proceeded with the rest of the flight testing program on that aircraft. Now we're starting to ramp up on the 19-seater program. We're going to see those aircraft flying next year. It's a very exciting time to be in this business in the zero-emission aviation. And on my last slide here is us kicking off the Jet Zero Council with the Prime Minister and a few others back earlier this year, when we were talking about how we're going to translate all that progress, all that vision into the actual aircraft of a meaningful size, commercially meaningful size by 2030. So it's great to be in the UK. We were originally started in California, but now most of the company is actually located in the UK. And we see a great support from the industry and from the government here, and we're very lucky to be here. So this is my last slide, and with this, I guess I'll take questions.
Thanks very much, Val. That was a great deal of information for us all to take in. I guess one of the favourite bits that I found was your description of the various alternative approaches, and why what you're proposing comes out at the top of the pyramid is at the top of the pyramid as your favourite solution. I'm going to go through the questions from the audience in slow time. I think we've probably got about 20 minutes, so let's see how many we can get in. First question. We're all very aware of the airship accidents in the interwar years. It's a common conception that hydrogen is very dangerous and has been avoided in atmospheric flight since that time. What's your view?
Yeah, of course, frequently asked question, as you can imagine. And in fact, so much that we at some time we actually had a slide with Hindenburg disaster, in our slide deck, so to just kind of lay that to bed early on. And the short answer is in 80 years that passed, technology has improved a little bit, and our ability to contain hydrogen and tame it has improved dramatically. Also, of course, in the case of a blimp, you look at the low structural integrity of the containment vessel. By construction, you cannot make it heavy, you cannot make it sturdy, because otherwise the thing's not gonna fly. So you have a lot of vulnerability just built into that. Contrast that with, for example, compressed hydrogen storage vessels that are used now in definitely over 50,000 ground vehicles worldwide, right? Material handling equipment, trucks, cars, operated by unqualified personnel, often, right? So personal vehicles, like the worst possible application. And we don't really see anymore any significant safety incidents in those cases. And the reason is there are multiple layers of safety that are built into the storage vessels and the vehicle systems. The storage vessels themselves are probably, once integrated for the compressed gas, once integrated into aircraft, are going to be the strongest part of the aircraft. Right? Really, they tested the testing procedure for those things. For penetration testing is firing high caliber guns at close range at those tanks and testing them for penetration. So really, the industry has moved quite a bit and is able to figure this out. And it's as Glenn Leveling actually first I heard he put it very, very well, and he's a VP of zero emission for Airbus. It's about the system, right? It's about safety system. Jet fuel is not a safe substance either. Okay, It burns, it explodes, and it does all kinds of crazy stuff. And you just need to handle it with respect, and you need to figure out the safety protocols, and it is entirely possible to do.
Yeah, I guess that's even more so for gasoline, for petrol in piston-engined aircraft. Okay, second question. Thanks for that. That was a good answer. When hydrogen burns, the product is largely water vapour. Is there a meteorological issue about the increasing number and density of contrails in the wake of aircraft operating at altitude, leading to further global warming through a blanketing effect?
Very good question. So, if you just basically exhaust that water vapor into the atmosphere at that high altitude, you would have significant effects, and you would actually exhaust, obviously, higher water content, especially if you replace the fossil fuel burning turbines with hydrogen turbines, for example, because the efficiency is rated 1-for-1, so you need to produce. You need to burn the same sort of chemical energy to produce propulsion, and now you don't have carbon, so you're producing everything. All the exhaust is water, right? With hydrogen fuel cells, the situation is quite a bit better, but still, you would be exhausting a lot of water vapor. Now, what you have a key advantage in the hydrogen electric side is that your exhaust is relatively low temperature, which means that you can actually condense the water. You can actually manage the water output of your system, and you can also manage what's the effective altitude of your water vapor exhaust. Right, so you can have condensation on board. You can have ice formation, controlled ice formation on board even. And those things haven't been, done and tested before, because this is all super new area. But you can have, water rejection managed in the hydrogen electric system much more effectively than in a hydrogen turbine or a classic turbine, because in those cases you have 1,000-degree exhaust. You can't do anything about it. This is a big part of your thrust generation. So it just goes out there, right? So hydrogen turbine, you would just do it. But with a hydrogen fuel cell, you actually have an ability to manage that water output quite effectively. And this is what I think will be a key part of high altitude operations.
Okay, thanks for that. I've got some detailed technical questions. If I strain my eyes to see the small print in the Q&A box, I apologise. Are you aware of any research using capacitors in place of or alongside traditional lithium batteries?
Yeah, well, people try to do these things. The problem with supercapacitors is that the energy density is quite low. Power density is of course great, but energy density is quite low, and you actually when you use them with the battery, you don't necessarily get a lot of advantage without a lot of power electronics, right? So if you, for example, do a hybrid parallelization at the cell level, you don't get a lot of buffering capacity, because the batteries are pretty stiff in terms of the volt amp characteristics. And the capacitors are obviously, energy proportional to the square of voltage, so your voltage degrades and then you hit the battery anyway. So in order to decouple these characteristics, you typically would need pretty heavy power electronics, DC-DC conversion mechanisms and so forth, which kind of defeat the purpose a little bit. It might be interesting to do this with maybe fuel cells, right? Because fuel cells generally have much more elastic VI characteristics, voltage current characteristics. So you have typically, open circuit voltage is over 1 volt, and full load voltage is 0.6, right? So you have an almost 2x difference, which means that from a super cap you can extract 75% of energy going through that, reduction, right? Cu squared. So that is an interesting potential to provide the burst power out of the fuel cell system. And of course, this is something that people who are working on high power fuel cell systems can look at.
Okay, thanks very much. Let's see the next one. Are there any major efficiency gains as fuel cells get very large, similar to how the larger turbine engines are much more efficient than the smaller ones?
Yeah, good question. You have some, not as dramatic as in the thermal engines, and I think some part of that is from the first principles is sort of volume versus surface type thing, right? So you produce energy, you produce electricity in the fuel cell on the surface of your membrane. Yeah, so you scale the power with the surface area. In the turbine engine, there is a significant sort of volume component to that, so you're able to scale faster, while your surface area does not need to increase linearly, and that makes thermal management easier, perhaps. So the increase of efficiency will be more gradual with size. But what the benefit that we have is on the fuel cell, the theoretical efficiency is much higher than any possible realistic thermal efficiency of the turbine engine. And on the sort of low heating value, calibrated to low heating value of hydrogen, the theoretical efficiency of fuel cells is up to 94%, right? And today, again, we have the cells that we are actually flying today are maybe at the most efficient point, a little over 60% efficient. At the realistic power points, probably around 55% efficient. But there are very well-defined avenues for improvement. Yeah. So we already see in some applications, like space applications, for example, you see cells 75% efficient. But of course, they're not really mass made, and you want to put them into commercial aircraft anytime soon. But the theoretical limits are up there.
Okay, super. Thank you. Next one. How does your Malibu, put the teeth back in. How does your Malibu fuel cells power lapse with altitude? Is it similar to a normally aspirated piston engine?
Good question. It is similar to a turbocharged piston engine, I would say, yeah, because every fuel cell powertrain has a compressor. Actually, pretty strong air compressor that you need to have in order to push the air through all of these reaction channels. Remember, the power out is proportional to surface, right? The figure of merit for the fuel cells is amps per square centimeter of membrane. Yeah, so you get the more power out of more surface. Now you increase the surface while managing the volume. You have longer and longer and thinner channels that you need to push the air through or push the reagents through. Hydrogen is not a problem. Hydrogen goes everywhere. Relatively low pressure differential. Air you have to push through, especially given that you're dealing with 20% partial pressure content, right? So most of it is nitrogen and a little bit of oxygen, and oxygen is what reacts. So you have a pretty sturdy air compressor that feeds the fuel cell, which means that you have automatic kind of compensation for altitude, similar to what you have in a turbine engine or a turbocharged piston engine. Now, at some point, it runs out of room, and you flat rate it to some altitude, and then after that you have the derating curve, but similar to every other engine. Okay, again, thank you for that one. Next one.
Would the hydrogen for fuel cells be stored in the aircraft as pressurized gas or in cryogenic liquid form? And there are several similar questions about which is the best, or I'll leave it to you to answer. The question is around liquid or gaseous.
Yeah, good questions. We think that for the first product introduction that we're planning in the next 3 years, we can get away with gaseous storage. And generally for, as we call them, slow and low airframes. And these are most of the airframes that you see there on the 10 to 20 seat variety, right? Most of the aircraft is more of a utility aircraft. It goes for relatively shorter distances, so it doesn't go to 30,000 feet on those flights. For those aircraft, low and slow, the penalties for the gaseous storage are not as significant than compared to the fast aircraft, fast and high aircraft. So we think that for the products, the first product introduction, the first commercial hydrogen electric planes, we can do it with compressed gas, which of course makes it much simpler from multiple perspectives, right? The safety is already well understood. The ground transport uses tens of thousands of vehicles with that type of approach. And from the certification standpoint, is much easier to do than a complex cryogenic system. But then when you go to the larger aircraft beyond, let's say, 20 seats, you would need to start introducing cryogenic storage, because you need higher and higher densities in terms of the volume of fuel that you need to store, or you can store in the airframe. And when they become faster, your volume decreases, or volume flexibility decreases, and you need to start having some trade-offs. So that's when you need liquid. But by that time, we think that both the safety aspects of liquid hydrogen storage in aviation will be better understood, and also the cost of production of liquid hydrogen will be significantly lower than today. So we think that the timeline of needing that and having that form of fuel actually practically available will coincide, and that will happen about maybe 6-7 years out.
Okay, thanks for that. I've got a question from our branch president, Jonathan Council, who works for IEG in the airline, or the airline group. Thanks, Val. Great presentation. Yesterday, the UK government announced, as part of its 10-point plan for a green revolution, existing support for the UK hydrogen economy. However, it looks like there will be many competing sectors demanding the use of hydrogen. Are you confident that aviation will be able to access a share of the valuable low carbon resource? Now, we've had lots of ticks against that one, so that's probably one of the most popular questions we've been asked.
Yeah, I think, for hydrogen, the more consumption, the better it is for the new industry, right? If you look at the economics of that fuel, it's driven by the capital on the zero emission side, right? We're not talking about the steam methane reforming and all that, right? Fossil fuel production. On the zero emission side, the hydrogen electrolysis or water electrolysis, the main economic components that go into the price of fuel at the pump are capital expense of electrolysis equipment and delivery cost, right? So, and in the capital expense of electrolysis equipment, the more volume you have on the offtake, the faster the cost drops. Yeah, because that's a classic, learning curve type equation. We saw it happen in PV. Solar panels, dramatic reduction over 10-15 years. We saw it happen on the wind turbines, dramatic reduction, and we're going to see that happen in electrolysis as well. And on the delivery cost, which is more sort of linear on the cost basis, we actually, as I mentioned, our approach is on-site generation of fuel. And again, we already have the first version of it here at Cranfield. We're about to scale it to several more locations to support our demonstration work and so forth. So I think, it actually helps to have more consumption, because that drives everybody's price of fuel down, right, and makes commercial introduction of these concepts more realistic, and with less government support requirements, right, which is of course important for scale eventually, because you can't rely on government support forever on these things.
Okay, we probably have run out of time, but there are so many questions, and this is a subject I really love. I think I'm really into this. So I'm going to ask a few more questions before I guess people will start disappearing now as they have other other bookings for their time. Henry Morris asked us the question: have ZeroAvia experienced any regulatory hurdles with your initial flights in the UK? Do you foresee difficulty working with the regulators in future regarding any certification?
Yeah, well, certification is of course a very big consideration here, and in fact easily the highest risk to our timelines to delivery to the commercial service. The technology side, we feel we have a pretty good handle on. The certification side, part of it is, there are no rule books, right? There are no public means of compliance, special conditions, whatnot for hydrogen electric power plants. So we have to, jointly create it. That will take some time. This is, of course, is on our project plan, and we actually work with the CAA, especially very, very closely. We worked with the FAA, so we had, first flights actually occurred. First battery flights for us occurred in the United States, so we had to work with FAA for flight permits, and then we moved the hydrogen program to the United Kingdom, and we had to work with the CAA on this. There were mutual learnings in the process, of course, but what we see is a very, very strong commitment from the Civil Aviation Authority here and the government from the top level down to new propulsion, to making sure that these new technologies get the right level of priority when we do talk to the regulators. Of course, it's going to be a lot of work because it's a new thing, and we need to make sure it's as safe or better than the incumbents, but we feel pretty optimistic given the level of support and attention. Okay,
as I say, we're well over the time limit now, but I'm going to go on. I'm going to challenge the world. What typical maintenance is required on an on a hydrogen electric powertrain?
Yeah, so we think that we can actually achieve, even on the small power plants, we can achieve 10,000 hours of endurance before major overhauls are required. And we're actually hoping that a lot of the maintenance work will be on condition because of the level of instrumentation that we have in the power plants. And the main service sort of item that we would see in this type of power plant is the fuel cell stack itself. That will have degradation of the membranes, will have some performance degradation, whether it's a actual material degradation or performance degradation. That will likely occur at the stack level. And we're designing our power plants so that we can actually have a very, very easy and modular way to service those components that does not take the aircraft out of service for a prolonged period of time, which will be quite important for the operators.
just check with you, Val. You haven't got something you're missing now, have you?
No, I'm good for another 10 minutes or so.
Okay, awesome technology. Are supersonic speeds possible with such hydrogen electric fuel cells?
Well, technically, yes. The problem is, of course, the power levels required are quite a bit higher, especially for sort of going into the supersonic, going through the barrier. Today, the fuel cell based engines or power plants have, as I mentioned, significant power density disadvantage, which means that for extreme power applications, it would hurt them, right? So the fuel we can deal with, right? So the energy part of the equation we can deal with because we can already see very high mass fraction storage with liquid hydrogen, for example. So we can store the fuel, okay? It's a matter of amount of power that you need to deliver. And because the power density of the hydrogen electric power plant is lower, significantly lower than a powerful turbine today, we're going to have a little bit of a headwind there. As we have the power density improving, then we have a better competition. So maybe 15, 20 years out, that could be a possibility, but right now it's a very tough thing to do.
Okay. Airports are usually in urban areas, which limits the opportunities for local renewable sources of energy. Perhaps local modular nuclear reactors for airports might be a more sensible base load power source. Not quite sure what that one is, but I'll leave that one with you. I'll read it again.
Oh, this would be outstanding. Yeah, and we're very excited. I was very excited about actually I think it was a Rolls-Royce announcement even last year about modular reactors. The concepts, and I hope that this becomes a reality. Now, of course, there are unfortunately a lot of political overtones around that one in particular. But again, technology has moved on quite a bit, and there are ways to do things safely. So local source of electricity is definitely key to the success of any hydrogen story, really. I think even if you don't have that, though, transporting electricity is dramatically easier than transporting hydrogen, for sure, and even fossil fuel a lot of times, because you can do it in a relatively dense high voltage cable network. Yeah, so the amount of land that you need, the environmental cost of that is generally significantly lower. So I'm pretty optimistic that even if we don't have local supply or immediate local supply, we can get electricity to the right points.
Right, I'm with it. I understand the question now. So what she was really saying is the electricity for the electrolysis of the hydrogen would come from a mini reactor. Yes, I'm there. I don't know if you saw in the news yesterday, but I see there's some contracts being let for those Rolls-Royce mini reactors.
It's great.
Okay, I think we've got to have the last question. There are so many, so I'm going to ask William, can he wrap some of the other questions up in an email to you and get you to answer some of these, and we'll put them out to our members when we can. Seawater. Can you use seawater, or do you need distilled water for the distillation process?
Yeah, so with the electrolysis systems that we have right now, we need purified water, and the water management components are integrated in our hydrogen production. So it's not a separate component; it's just a part of the plant, if you will. But there are very interesting developments out there that actually have the electrolysis designs that operate on seawater directly. They're not in mass production yet, but there are some interesting developments, of course. Now, actually, in terms of the water consumption, because sometimes we do get this question on the, well, there's shortage of fresh water, and how do you think about that? In fact, that's not a problem at any degree here, because the amount of energy that is required to split water into hydrogen and oxygen is so much greater than the amount of energy that would be required to desalinate water for that process, that you could just have a desalination part built in, and that would be like a very small percentage of your total energy requirements for hydrogen production. So in a worst case scenario, you can have the salt water coming in, desalination system, and then pure water going into electrolysis, and that would be only very minor impact on the energy intensity of the process.
Right, so for watchers who have asked questions, we're 15 minutes overrun now. I've got to stop. I'll get William to wrap these up and email them on to you and see if we can get an answer back for the ones we haven't answered. Okay, so on behalf of the committee and the members of the Heathrow branch of the Aeronautical Society, Val, I must thank you for giving up your valuable time in order to tell us all about the possibilities of hydrogen fuel cell powertrains as applied to the future air vehicle propulsion system. I wish both yourself and the ZeroAvia company the greatest technical and commercial success in this area. I think we all can now see that you're bidding to be the next engine OEM rather than an integrated vehicle solution. I'm going to thank William, our Honorary Secretary, for undertaking the administration which made this lecture possible tonight. Without him, we'd be struggling to get teams to work sensibly. I also wish to thank all the members of the audience, those attending tonight's lecture. I hope you've all learned as much as I have. It's fascinating. I'm an old, I nearly swore then. I'm an old person, and I can see how exciting this is for young people. I wish I was at the beginning rather than the end of my career. For all of you out there, please keep a note in your diary. There'll be a second branch lecture webinar this month, which will be entitled The European Green Deal, Opportunities and Risks for Aviation. It'll be presented by Valentina Vecchio, EU Government Affairs Specialist at the Boeing Company, and will be transmitted live at 1 o'clock UTC on Thursday, the 26th of November, next Thursday. The presentation will focus on EU sustainability policies, the European Green Deal, and the opportunities for aviation climate strategy. Watch out for the calling notice from William and book your seats now. Keeping up the sustainability theme, our fifth and last lecture for 2020, the December lecture, will be presented by Mike Durham, the Chief Technical Officer at Hybrid Air Vehicles, and he will discuss their efficient and sustainable Airlander airship. It is currently scheduled for transmission at 12 o'clock UTC on the 10th of December. Again, watch out for the call-in notice from William and book your seat as soon as you can. Finally, I look forward to seeing you all again very soon. I wish you all good health and good luck for the rest of the year. A happy Christmas and a very successful 2021. Val, thank you for giving up your time. I think people out there who aren't as up to speed on the new technologies as perhaps they should be by now, I think they've learned a lot tonight. Val, thanks very much indeed. I'm going to hand you back to William. Thanks again.
Thank you, Peter. Thank you, the members of the society, and thank you, William, for managing it all.
Oh, thank you, Val. So, ladies and gentlemen, our tonight's session is come to an end. As I have mentioned at the beginning of the webinar, this session has been live recorded, and we will publish it on our YouTube channel and podcast next week. And you can also search RAeS Heathrow branch on the above social media channels: Twitter, Facebook group, LinkedIn group, and YouTube channel. Also visit aerospace.com/Heathrow for more information and our latest event. And thank you very much, ladies and gentlemen, and good evening to you all.
From across the globe, from the center of aerospace, and now to you.
Thank you for downloading from the Royal Aeronautical Society. If you enjoyed this content, please consider showing your support for the Society. Share a link to this presentation by email or on your favorite social networks. If you have an interest in aerospace, consider the professional and personal benefits of membership. Visit www.aerosociety.com.